So far we have looked into reflection and refraction, which govern the macroscopic interactions of light with matter. Now we will venture into the realm of diffraction mechanisms, which govern the microscopic interactions of electromagnetic waves like light. The learning objectives for this video involve obtaining a basic understanding of the diffraction of light. We will discuss the concept of interference and apply it to electromagnetic waves. Finally, we'll consider the application of interference in solar cells. As we trail towards some of the more complicated quantum mechanical properties of light, it is good to know that every cloud has a silver lining. A phrase coined by the English poet John Milton in 1634. Silver linings are a phenomenon well demonstrated by this picture of the sun, hidden by clouds. But why do clouds have a silver lining? And which properties of light underlie this phenomenon? The silver lining of clouds is an example of diffraction. This illustration shows that direct light beams propagating through a cloud will be absorbed. Only the beams at the edges of the cloud are diffracted towards the observer at the ground. The edges of the cloud therefore appear bright white. Diffraction can be defined as the bending of light around an obstacle. Diffraction can occur when light encounters particles that have a size of the same order of magnitude as the wavelength of light. A cloud consists of many water particles. The illustration shows two such water particles in dark blue, partly blocking an incident light beam. The light wave will propagate between the water particles. The area between the water particles will actually function as a point source from which the light wave will propagate in all forward directions. Therefore, a fraction of the initial light wave will be diffracted towards an observer on the ground. This point source function of the area between the water particles is better illustrated by the single slit experiment. In this experiment, a uniform light beam propagates towards a solid wall containing a single slit. The colors represent the amplitude of the electrical vector of the wave. The slit has a width equal to the wavelength of the incident light. We can clearly see that the light propagates in all outgoing directions and is not limited to the width of the slit. The intensity decreases with increasing angle from the normal. The single slit causes a familiar wave pattern of light intensity on the black wall. This pattern in light intensity is shown on the right. But what happens when we introduce a second slit, also with a wavelength size width? What we see is that two waves start to interfere with one another. The uniform outward moving half circles are now broken up into peaks and troughs. These peaks and troughs also appear on the black wall. We find the same familiar pattern of light intensity, but now broken up into bright red peaks and dark troughs. This phenomenon is known as interference. Interference occurs when two different waves occupy the same space at the same time. We call these waves superimposed. This figure shows two superimposed waves moving in opposite directions. The resulting wave is depicted by the blue line. We can see that the amplitude of the superimposed wave is sometimes greater than and sometimes smaller than that of a single wave. When the two peaks of two waves are perfectly aligned, they are said to be in phase. Two waves in phase exhibit constructive interference. The amplitude of the peaks and troughs of the waves will then add up. This constructive interference occurs when the phase shift between the waves is 0 or 2 pi. When the peak of one wave aligns with the trough of the second, they are in antiphase. Their amplitudes will then cancel each other out. This occurs when phi is an uneven number multiplication of pi. By cleverly designing solar cells, we can use the concepts of constructive and destructive interference to our advantage. This is done, for example, in the so-called anti-reflection layer. The optical thickness of this layer is chosen such that the superimposed waves resulting from the reflection at the front and back of the anti-reflection layer exhibit destructive interference. This effect is shown in this figure, where the wave reflected from the first interphase and the wave reflected from the second interphase are in antiphase, at a phase shift of an uneven number of pi's. As a result, the total amplitude of the electric field of the outgoing wave is smaller, and therefore the total intensity coupled out of the solar cell is smaller as well. The phase shift, delta phi, is equal to the wavelength times the optical path length difference. For waves of a certain wavelength to destructively interfere, at normal incidence, the product of the thickness and refractive index of the anti-reflection layer have to match 1/4 of the intended wavelength. As we discussed in the section on the Fresnel equations, the optimal refractive index for a Rayleigh film equals the geometric mean of the refractive indices of the encompassing media. Assuming the encompassing media are air and silicon, the optimal refractive index is around 2.1. Let's say we want to optimize the destructive interference for the 480 to 560 nanometer wavelength range, the spectral range in which the solar spectrum has the highest value for the spectral power density. We can now use the relation we found in a previous slide to calculate the optimal thickness. For optimal performance, the anti-reflection film thickness should be between 60 and 70 nanometer. Now, in summary, we defined diffraction as the bending of light around an obstacle. We looked at the famous single slit experiment and saw that opening a second slit would lead to wave interference. A phase shift of 0 or a multiple of 2 pi leads to constructive interference, while a phase shift of an uneven number of pi's leads to destructive interference. Finally, we saw these concepts applied in solar cells through the use of an anti-reflection layer. I'll see you again in the next video.